x and y. The domain we usually say is the input, or we normally think of it as the x values. And range, if we talk about input output, range is what you get out of the function, so we say that's the output. Or for us, they're normally talking about y values, but just know, especially like in story problems, not always x and y, but the x is what you put in, it's an independent variable, but y is what you put out, it's a variable. Alright, so we define that function on Friday, and this is like the book definition. It is a relation where each element of the domain is paired exactly with one element of the range. Or, it's a nice way to remember how to tell something's a function. What can't repeat? The x's don't repeat, and that's what I have here. All the x's are different. For every x, I don't know where to put this. For every x, it only matches to one y. The y's can repeat, all the y's can be the same, but the x's cannot repeat themselves. Alright, so in the past, in Algebra 1, that's what you care about. Is it a function? Is it not a function? There are two more specific types of functions that we like to talk about. One of them is called a one-to-one function. And so to be a function, all the x's just pair with exactly one y. To be a one-to-one function, all the x's pair with one y, and all the y's only pair with one x. And so I wrote all the x's are different, and all the y's are different. So if it's one-to-one, none of the y's repeat, none of the x's repeat. Okay? And an on-to function is a function where all y values are used. And I'm going to show you some examples of some things that are on-to and that aren't on-to. Most functions that we think about right now, most functions are on-to. Right? Not all functions are one-to-one. Most functions are on-to, but I like Googled some stuff so I could think of examples of things that aren't on-to that aren't just like x bar charts. Okay? So I don't think this is on your paper. Is this on your paper? It's not, right? So I wanted to look up some examples. Can you see that, or I need to make it bigger? Like this. How about that? Can you see that? So, a one-to-one function, really easy to see when you have like the mapping or the set, is if all the x's are different and all the y's are different. So this is an example of a not one-to-one function because you can see the y's repeat themselves. Or if two x's go to one y. This is one-to-one because for every x, there's exactly one y. Another way to think about a one-to-one function, what was the little test that we do to tell us something's a function? Like if it's a graph. The pencil test, the vertical line test. Vertical line test, you're checking to make sure all the x's are different. So this is a function, yes? If you want to check if all the y's are different, which way do you think you have to turn your pencil? So we can call it the horizontal line test. If I turn this side to side, is it going to pass the horizontal line test? No, so this is a function that is not one-to-one because if I drew a line right here, two of the y's are the same. And so you don't really have to know the horizontal line test, but I just wanted to kind of show you as an easy way to check to see if something's one-to-one is all the x's have to be different, it passes the vertical line test, and all the y's have to be different. Oh, I think that's what's done. Oh, yeah. So let's think about that for these. Again, not on your notes, but still something to think about. So what about this first one? Do you think this is a one-to-one function? Does it pass the vertical line test? Yes. Does it pass the horizontal line test? Oh, you think this has like more than one thing, right? Like you're thinking that it's a straight line there. It's really not. It's just like curvy. But I see what you're saying there. It kind of looks like it flattens out, but it's just a really small number of changes. So this one is 1-to-1. What about this one? Yeah, we just did that one. This one is definitely not 1-to-1. because it fails right there, right? It has 2 of the same y's. What about this one? Definitely not 1-to-1. It's kind of crazy. We're going to graph some of this stuff next semester. That looks exciting, right? But this does not pass the horizontal line test, so this one is also not 1, 2. Where even is it? Okay, an on-to function. So I haven't taught Algebra 2 in a long time, like 4 years probably. I think how old you were 4 years ago. You were just little babies. And I remember the last time I taught an on-to 1-to-1 function. Almost every function they show you is an on-to function, especially if they give you an equation. And so it was always like, what isn't an on-to function? So I wanted to make sure I looked up and asked you, or to show you what isn't an on-to function. So an on-to function, if they just give you like the mapping like this, it's easy to show it's not on-to function because all the y values have to be used. So you can see how on this one, the 1 maps to A, the 2 and the 3 both map to B. So every y value is used. So this is on-to. Here's an example where it's not on-to, where this C isn't used, right? So A and B have a match, but C doesn't. So it's not on-to. But how would that look as an equation? And so I did some Googling. What do we do in the world without Google? We didn't learn as much, that's for sure. So it says, is the function x squared, is that on-to? And f of x is the same as saying y. Well, that y equals x squared. So to be on-to, all the y values have to be used, or basically the range needs to be all real numbers. So the function f is not on-to because you could never get a y value of -1 out of that. Does that make sense? So a not on-to equation is an equation that has some y values that are never given. So linear functions, they go on forever in both directions, so they are on-to functions for the most part. So this is a concept that we don't talk about that much. I talked about it when I took this college class, and I feel like I learned a lot more about on-to functions then, but I just wanted to give you an example of an equation that is not on-to. Right? Okay. So moving on to the stuff that you have to do today. There's a lot of directions on this. You gotta check this out. Right? So, starting with just a relation. A relation is not a function in terms of, like, it's not an equation that goes on forever. But it could still be, like, past the 1-to-1 on-to test. So it says, state the domain and range of the relation, then determine whether it's a function, are all the x's different. If it is a function, is it 1-to-1, on-to, both, or neither? Kind of just getting you used to these vocabulary words. So these are just a bunch of points. So hopefully you feel good about this, maybe not. But what do I do to find the domain of just a bunch of points? You just put the x's. And it really doesn't matter what order you put them in, but I usually try to put them in order from smallest to biggest. Not that you have to. So I'm going to start here at -4, and I'm going to put little squiggles. I'm going to say -4, -3, that'll be that one, 0, 1, 3. So I have 1, 2, 3, 4, 5 points, 5 x's. And we could go ahead and say it is a function, because all the x's are different, right? So we can go ahead and do that over there. Alex is so excited to say, yes, it is a function. If x repeats, it is not a function, which means it cannot be on-to or 1-to-1 if it's not a function. The range is the y value. So again, whatever order you want, but I'm going to start with the lowest and go up. So I'm going to start with -2. And then I'm going to go 0, 1, 2, 3. So list the domain and range. Is it a function? We did that part. New part that you didn't do in Algebra 1, we want to say, is it 1-to-1? Is it on-to? Is it both? Is it neither? 1-to-1, are all the y values also different? Yes. On-to, are all the y values that have points on them, are they all used? Yeah, and so this one's kind of weird because it's not an equation, but because it's just points, as long as every y in our range is matched to an x in the domain, they are, we can say it's also onto. So we would say here that it is both one-to-one. And again, most things, I don't want to say always, but most things are one-to-one and onto. Questions about that? So most of what we deal with are not just points, we deal with lines. So we want to talk about some vocabulary there. A discrete relation, discrete means it has breaks in it. So like the one that we just did, it's not just a connected line, it's just dots. Okay, that's discrete. And most of what we do in math class, we talk about continuous relations, meaning that we can connect them with a line. The domain would have an infinite number of elements because it just keeps going, right? You put arrows on the end of your line to show that it just keeps going. So just an example there. A discrete relation is just dots. A continuous relation is connecting them. Equations is a continuous relation. Dots. We talked about this, I think. Didn't we talk about this, the vertical line test? No. We did? We talked about vertical line test? I meant on Friday, though. But a vertical line test is a great way to test if something is a function. And again, you're checking that each vertical line, pencil does, each place that you put your pencil would only touch that graph in one point because the x only shows up one time. But if you have like a sideways parabola, this is not a function because you can see right there that the same x value is used twice, so the x repeats itself. So that's a really quick and easy way to tell if a graph is a function. And then I even kind of showed you this horizontal line test that usually you don't learn about. So you're the same. Okay. So let's talk about these equations, and maybe, hopefully, you have some really good memories about how to graph linear equation, but if not, I'm going to review some stuff with you. And this week, we're going to talk about all the stuff that you learned about linear equations. Over like 2 chapters, we're going to do it in like 2 essays. Slope-intercept form, point slope form, finding slope, standard form, x-y-intercept, all that stuff. All right? So, y equals 3x minus 1. It says graph it and determine the domain and range. Then determine whether the equation is a function, is one-to-one, onto, both, or neither, and state whether it's discrete or continuous. It's a lot of direction, so make sure that, especially on the homework, that you're reading, that you're doing everything that it says to do. So if you remember how to graph this, the good old y equals mx plus b way, by all means go ahead and do that. But if you don't remember how to graph that way, remember that the go-to way, the first way that you learned how to graph in Algebra 1 is if you don't know how the graph's going to look, you can make a good old XY chart. Remember Ms. Vi teaching you an XY chart? Yes? No. Yes. XY chart means you can pick anything you want for X, and you plug it in and you find the Y that goes with it. What's your favorite numbers to pick? I usually pick, she said 0, 1, 2, that's a good one to pick. I usually pick -1, 0, +1. They're easy. Lots of people hate negatives, so they pick 0, 1, 2. Those are good ones to pick too. You could pick 7. You could pick 1,000,000 if you want. I don't have 1,000,000 on my graph here. I'm not even going to pick 7, Alex, because I don't even have 7 on my graph. Right? I know, I'm just saying. These are my favorite numbers to pick. So if I plug -1 in there, right, this is what we mean by independent variable and dependent variable. You can pick whatever you want for x, and y is dependent on what x is. Because if I plug -1 in for x, I would get -3 minus 1, I would get -x. But if I plugged in 0 for x, y now becomes 0 minus 1, which is -1. Right? That works with any equation. We're going to work with lots of equations this year. And any equation, if you don't remember what it looks like, you can always make an XY chart. I plug 1 in there, I get 3 minus 1, which is 2. You can calculate it. And I can graph those points, x and y. So -1, -4 would be right here. 0, -1 would be right here. And 1, 2 would be right here. And maybe you remember slope-intercept form, where you could start with a y-intercept of -1 and a slope of up 3 over 1, and you did that a lot faster than me, and that's okay. But we're not reviewing that yet, not till tomorrow or the next day. So I just want you to know that XY chart does work. This is an equation, so these are not the only 3 points on the line, right? This just gives me a guide. So then I want to connect it the best I can in a straight line. Doesn't have to be perfect. Oh, well, that's just... It was straight until my graph moved. I've had a lot more years practice than you, right? I put arrows on the end to show that it keeps going. That's why you could pick whatever you want for x, and we'd get the same graph as long as you plugged them in correctly, because all the points that match that line work. So, we can go to the end here. Is this discrete function or a continuous function? Continuous. All the equations for linear graphs will always be continuous because they make a line. What about listing a domain and range for an equation? Can we list all the x values that are on that graph? All right, go out. Is the domain just -1, 0, and 1? No, because this is also a point on the graph, and this is also a point on the graph. And if I kept going, this is also a point on the graph.
Alex!
Colton. He's right. It's infinity.
I know, but I was trying to see if you talking.
Settle. It is all the x's. If your graph is continuous, the domain goes on forever. All the x's are used. So, the domain you cannot just say is -1, 0, and 1. It's all of these. So we want to say all real numbers. So there's 2 ways to do this. In interval notation, I think this is the best way to write this. -infinity to infinity. All real numbers. If you're going to write this in set notation, you got to use some fancy math symbols. Ready? So remember, for set notation, we do x such that we want to say that x is a real number. So I guess you could get away with writing out x is a real number, but I'm going to show you the fancy notation, right? We're going to say x is an element of, so you do this little fancy E. It's like a C with a line in it. And then the symbol for real numbers is like an R with a double bar. So you do like R, 2 bars, like that. And that says x is a real number. That's fancy, isn't it? You can also just say x is a real number. I'll count that right. I just like to teach it. I think this is the way to go, right? Like, I'm an interval notation. What about the y values? Can we list out all the y values that are used? If there's an infinite amount of x values, could I write out all the y values that match up to those? Because if this just keeps going, right, isn't all these y values going to be used in this direction? And if this keeps going down, all the y values are going to be used? So the range is also all real numbers, which we can say -infinity to infinity.
How do you write it?
For the range, the same, exactly, the same thing, but you're going to use y. You can say y is an element of the real numbers.
We should just use staple to your
1-to-1, both, or neither? 1-to-1, does it pass the horizontal test?
Yes.
Definitely 1-to-1. On 2, is every y value going to be matched up with an x value? Yeah, because no matter what y value you can think of, there's going to be an x value that matches up to it. So again, the reason I wanted to show you specifically things that aren't on 2 is because so many of these are going to be both 1-to-1 and on 2. So I don't want you to think that everything is 1-to-1 and on 2. I think about this so hard. Like story, on edge, a little bit. All right. So you try this one. If you haven't already, I know you like to jump ahead because you're so excited about graphing. See if you can graph this and answer those same questions about the domain and the range, 1-to-1, on-to, both, neither, continuous, discrete. Ready to go. The XY chart if you need to, or if you're in this one, this one, you want to calculate that works too. That's where you already have a better look at it within there, right? And here's the other ultimate experience. Or it's a lot better. You're on the right track. Good old Matthew McConaughey quote. Right, I saw lots of people making the chart, so that's a good thing. You should, if you pick -1, 0, and 1, get y values of 3, 5, and 7. If your x values are different than mine, then your y values are going to be different. But what should be the same is our graph should end up in the same spot, which I think should look like this. So some people made their whole graph filled up with lines. That's awesome too. Remember that this is a line, so that's why it doesn't matter what points you make, because when you connect it, we should all have, a similar graph because we're sketching it. So Chandler, what do you think about the domain on this one? Because it's a linear equation and all the x's are used, yes? Wes, what do you think about the range on this? Also all real numbers. Is this a function? Yes. Is it 1-to-1, on-to, both, or neither? Also both. And is it discrete or continuous? Continuous because right? Kind of just getting used to those vocabularies. Alright, the last thing I want to talk about is function notation. When we talk about functions, we usually write them in function notation. And all function notation does is instead of using y equals, we replace that y equals with an f parentheses x. And remember that that's read as f of x, which means like a function of x. And as you probably remember from Algebra 1, you don't have to use f. It could be g of x. It could be h of x, right? They usually use letters around f, not always. But we just read that as a function of. So when you see function notation, you know it's a function right away. And it's just kind of some notation that's helpful, especially some of the stuff that you haven't learned yet that we're going to learn this year. So instead of writing y equals f of x, sorry, 5x minus 1, you can just change that to f of x equals 5x minus 1. And just know that y and f of x mean the same thing. So instead of saying y, you can say f of x. So for now, all you need to know is that it means f of x and y, and that if they give you an x value to plug in here, all you do is you plug it in. So let's look at those last examples here. Okay, easy one, a little more difficult one. So if I gave you f of x equals x cubed minus 3, find f of negative 2. You need to know that that means plug in negative 2 for x. So instead of saying like find y when x equals negative 2, math people have created this lovely notation that all they have to do is say f of negative 2. So that means everywhere I see an x, I'm going to replace it with negative 2. I don't do anything to this side. I'm not solving for f. F is not a variable. I'm just saying the function when x is negative 2. And then on this side, I'm going to plug negative 2 into that problem. Every function notation. And I don't care if you use a calculator on this. I'm going to leave the thing side over here. I don't do anything. But negative 2 to the third, remember, is not negative 6. Negative 2 times negative 2 times negative 2, which would be negative 8 minus 3, which would be negative 11. One reason we like function notation in math is because this gives me when x is negative 2, the y value is negative 11. So it's like giving me a point on the graph. You could just say negative 11. I'm okay with that. But I just wanted you to see that like when x is negative 2, y is negative 11. So that's what function notation gives us. Austin, you have a question? So how can we raise the bar a little bit and maybe do a little more complicated stuff? What if I gave you a letter and a number to plug in, or just a letter? So look at this one. Same equation, but now I want you to find f of 2t. Well, 2t is not going to just give me a number. I'm going to get an answer with t in it. So over here, I'm going to replace x with 2t. So here I'm going to have 2t to the third minus 3. And this really doesn't help me when I'm graphing, because how do I graph t? But it's just to kind of practice that algebra there. So remember our rules of exponents. You have to take everything to this third power. So 2 to the third, just did up there, negative 2 to the third. 2 to the third is 8. 2 times 2 times 2. And t to the third, I can't do anything but write that as t to the third. And then I subtract 3. Can I combine 8t to the third minus 3? No, I can't do anything else, which means that's my answer. If you want to write f of 2t equals this, that's it. So if they give you a letter, know that you're going to have a letter in your answer. If they give you a number, you should have a number as your answer. You don't have to, no. Is that my last example? So I made a lovely worksheet for you. No. But I can put one on there if you're looking. Okay, so 1 through 4 are giving you equation or relations that are in the little chart or the x-ray chart. You have to think domain at range is a function like 1 to 1 on these both two, just like what we started with. 5 and 6 are equations, just like what we talked about. 7 through 12 are function notation. Maybe some work on 7 through 12. And then on the back side, I gave you 3 problems